Okay, we are going to do one final example of graphing a polynomial and finding its root. I'm going to make it intentionally fairly complex. So let's start. F of x equal x to the power 6. I said it's complex, so degree 6 polynomial. 3x5 plus 2x to the power 4 minus x squared minus 3x minus 2. We have to find the roots and we have to graph it. All right, let's get to the business. What do we know? Anytime you see a problem like this, just do something. Think through, try something, and sometimes you have to come back. So let's see one thing we know. We know, for example, my first technique and behavior. We have talked about when you have to plot a graph, think about end behavior. When x approaches infinity, y approaches what? Well, all these terms here do not matter. The only one that matters is this. So what happens when x has become very large? Well, y is going to become very large, so y approaches infinity. When x, on the other hand, approaches minus infinity, y, which is x to the power 6, it doesn't matter whether it is positive or negative, and once again, that approaches infinity. Make sense? So we know because of this term, which is the degree of this polynomial, it is positive coefficient 1, tells me that the end behavior is such that the graph, I don't know what the graph will look like, but I know it will end somewhere here and it will end somewhere here. That's one thing we know. Okay, what else do we know? Well, the second thing we know is, let's call it y-intercept. So f x equals 0 is simply minus 2. So I know somewhere this graph is at x equals 0. I know this point. What else do I know? I don't really know much at this point. So let's try. Let's try third thing that we approach. One is sign change. F of x has how many sign changes? I'm going to write it again. x6 plus 3x5 plus 2x4 minus x squared minus 3x minus 2. Let's see how many sign changes. This is positive. This is positive, positive, negative, negative, negative. How many sign changes we are talking? One sign change. That's it. Nothing else. That means this tells me there's only one positive real root. We know it's one because it can't be, we know there's one sign change, okay? But with minus x, look what happens. F of minus x. Now, what I'm going to do here is that I'm going to take the same coefficients, but I'm going to replace x with minus x. So it's minus x to the power 6, 3 times minus x to the power 5, plus 2 times minus x to the power 4, minus x to the power square, minus 3 times minus x minus 2. Now lots of minuses here, so let's be careful. Well, minus x to the power 6 is simply x6. Minus x to the power 5 is minus x5, so this coefficient sign changes. Minus x to the power 4 is only x to the power 4. This minus x to the power square is x squared, but the sign here, that makes it same. This changes, 3x minus 2. So in general, what I found is that when you have the odd powers, sign changes, like Here, there's an odd power. Sign changed. Here, there's an odd power because it is x to the power 1 sign change. But if you notice, this is even power, no sign change, no sign change, no sign change, and no sign change. Okay? Let's remove some of these circles, otherwise it can cause confusion. All right? So, now let's count the sign changes. How many sign changes do I have? This is plus, this is minus, this is plus, this is minus, this is plus, this is minus. Well, sign change, sign change, sign change, sign change, sign change. How many sign changes we have? We have 5 sign changes. So that means there are 5 or 3 or 1 negative real root. And we have talked about why it's going in steps of 2, because if there is 5 real roots, great, there's 5 real roots. But if there are 3 real roots, well, that's because the other 2 are complex roots, and complex roots always come in pair. So this is good. This is good. So I know some idea. There's 1 positive real root and there are 5, 3, or 1 negative real root. By the way, one thing I knew, because it's a polynomial of degree this, I know it will have the degree equals 6. That tells me it has 6 roots. Some of the roots will be complex, some of them could be real, some roots could be multiple times, but I know there are 6 roots. Okay, let's see. The fourth thing which we know is we know the rational root theorem. C over D, if there is a rational root, it is going to be a factor of -2, which is coming from that last coefficient right here, divided by 1, which is coming from this coefficient 1, right? So it is actually plus -2. Well, so what are the factors? Plus -2 factors divided by 1, that's trivial. Well, what are the factors of plus and -2? Well, it is +2, +1, -1, -2. So I have these as possible candidates. We don't know this, whether it will work, but they are candidates. So let's try. I'm going to go and copy this polynomial. And let's clean this puppy here. So I had x to the power 6. This was my polynomial, right? Well, let's just capture this now, all this stuff here. And I can see, copy. All right. There we go. Looks good. Okay, that's my polynomial. Well, let's try f of 1. I'm just gonna go fast. 1 to the power 6 is 1, plus 3, plus 2. Since it's 1, -1, -3, -2. I like it. It's looking good. So if f1 equals 0, well, that's worked nicely. So that's one candidate. Well, let's try f of -1. X to the power 6 will be 1. X to the power 5, -1 to the power 5 is -5. So it's going to be -3 plus 2 -1 -3 times -1 -2. Well, 1 -3 plus 2 -1 plus 3 -2. Well, this is looking good too. 2 and 2 cancel, 3 and 3 cancel, 1 and -1 cancels. So that gives me this equals 0. So my roots are 1 so far, and I found -1 to be root. Okay? Let's try f2. Well, that's 2 to the power 6 plus 3 times 2 to the power 5 plus 2 times 2 to the power 4. There's no way it can be 0 because this is a huge number. That's 2, 4, 6. That's almost 32. And I have 3 times 16 and 2 times 16, right? It just, actually, this is 64. I'm wrong. So the point I want to make is that before you even do your calculation of 2 squared minus 3 times 2 minus 2, look at that. All these are positive terms. They are not going to have enough negative terms, so this is not equal to 0. Forget about this. But let's try f minus 2. That has some hope. Well, that is minus 2 to the power 6 plus 3 times minus 2 to the power 5 plus 2 times minus 2 to the power 4 minus 2 whole square minus 3 times minus 2 minus 2. Well, what do I have? 2 times 2 is 4 times 2, 8, 16, 32, 64. Minus 2 to the power 6 is 64. But this is minus 2 to the power 5, so it's minus 32. So it's plus 3 times minus 32 plus 2 times 2 times 2, 4, 16 minus 2 squared is minus 4 minus 3 times minus 2 becomes plus 6 minus 2. So that is 64 minus 96 plus 32 minus 4 plus 6 minus 2. I think I'm liking this because look what happened. 64 and 32 is 96, which cancels. Minus 4 and minus 2 is 6, which they all cancel. So this ends up becoming equal to 0. So that means minus 2 is a root. Okay? So now I've found 3 roots. Well, what does that tell me? Well, let's try. I know that means, remember we had edit. I'm going to paste that baby here, and there you go. Remember, this was our polynomial. This equals x minus 1 times x plus 1 times x plus 2 times some new polynomial called qx. And the reason I'm saying is this tells me x minus 1 is a factor. This tells me x plus 1 is a factor. And this tells me it's x plus 2 because I'm doing x minus minus 2, correct? So I have these. So I can say qx equal fx over whatever I have here. Now let's simplify that first. X minus 1 times x plus 1 times x plus 2. All these two guys, a minus b times a plus b, gives me a square minus b square times x plus 2. And if I multiply these, I get FOIL. First in, that's x cubed multiplied by this plus 2x squared minus x minus 2. All that goes here, right? So what this is telling me is that I have a this polynomial goes here, right? Now let's get rid of these extraneous arrows and all that. Okay? So that's pretty cool. Now what do I do? Now look, fx has a degree 6. It's being divided by a polynomial with degree 3. Approximately, not approximately, the net polynomial qx will be degree 3. Well, that's good. We just reduced a beastly, monstrous, huge degree 6 polynomial to cube. Cubes are almost close to quadratic, and quadratic we know how to solve, right? Okay, so what do we need to do? It's a long thing, but let's do it. Let's do it. Let's just do this division where we are going to divide the big polynomial that we have with by this little polynomial that we have. And what was the big polynomial we had? Well, this is our big polynomial, right? I'm going to just divide the whole big polynomial with this little polynomial. And let's get going. Huge, huge polynomial. I'm just going to move this just to create more space. All right, so that's good. Okay, that's very good. How do we do it? Let's do it. Okay, I'm going to use different colors here just to bring some more clarity. All right, done. Now, I have that. Let's do. Well, first is x cubed needs to go in x6. Well, that is x cubed, correct? Let's multiply x cubed with this. What do I have? I have x cubed times x cubed is x6. X cubed times 2x squared is plus 2x to the power 5. X cubed minus x is minus x4. And this is, it gets tricky, is x cubed times minus 2 is minus 2x cubed. And where is minus 2x cubed? It's not here in the on the top, but it has to be here, right? And if I do this and I do subtraction, let's use black color again. Well, let's use red or purple. See, this cancels. 3x5 minus 2x5 gives me x to the power 5. Actually, I want to just separate this. It gives me x to the power 5. 2x4 minus x4, this becomes plus. It gives me 3 plus 3x4. Minus, see, there is no cube here. This cube is missing because it is saying 0x cubed. I still, however, have to subtract. So 0 minus 2x cubed, this becomes plus. This is 2x cubed minus x squared, right? Okay, so that's good. All right, then next step, what do I need to do? X cubed goes into x5. It's x squared times, let's repeat the process. X squared times x cubed is x5. 2x squared plus x multiplied by x cubed is plus 2x4. X squared minus x, so it's minus x cubed minus 2x squared, correct? And now if I do minus, 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 plus, plus, what do we get? X5, this cancel. 3x4 minus 2x4 is x4. 2x cubed plus x cubed is 3x cubed. Minus x squared plus x squared is plus x squared. And I'm going to borrow minus 3x minus 2. Correct? Let's try one more time. X cubed needs to go x4, so this is x. So what do I get? X times x cubed is x4 plus 2x cubed minus x squared minus 2x. Correct? If I change the signs, minus, minus, plus, plus. And what do we have? This cancels. 3x cubed minus 2x cubed. Actually, let's use 3x cubed minus 2x cubed is x cubed. X squared plus x squared is 2x squared. Minus 3x plus 2x is minus x minus 2. And notice how this is same as x cubed plus 2x squared minus x minus 2. That means all I have to do is multiply by 1. And you can see, hard to see. You see how this is the same? You see that? So all I get is the same stuff. I get x cubed plus 2x squared minus x minus 2. And this, by the way, is a very good sign because that tells me everything is canceling out. 0. That means no remainder left. So just remember, we took the big polynomial of degree 6 here, this polynomial. We divided by these 3 factors we got, which is x cubed plus 2x squared, this thing, and we got this new polynomial. That means I have my fx. I want to reduce the zoom of it so I can see. It's kind of getting big. So this fx, which we started with fx, which was x to the power 6 plus 3x5 plus 2x4 minus x squared minus 3x minus 2. And we are saying this equals, remember first root was minus 1, so it's plus 1, so it's x minus 1. Second root was x plus 1. Third root was minus 2, so it's x plus 2, multiplied by what we got here, which is x cubed plus x squared plus x plus 1, right? Right? Now, how can we factor this? Well, there are a couple of ways you can try that. First, remember we started with n behavior and c over d and sign change? Well, same thing can apply to this new polynomial qx, right? I can do that. I can apply that. For example, I can say sign change in fx, in qx, sorry, we are dealing with qx. So fx has no sign change. Everything is positive. That means no positive real root. But if I'm using the not fx, it's qx. But if I say q minus x, what is that equal to? Well, that's minus x cubed plus x squared minus x plus 1. Remember, only the odd power changes in sign. And if I look at the sign changes here, one sign change, second sign change, third sign change. That means it has 3 or 1 negative real root. Well, let's apply C over D. C over D are factors of 1 divided by factors of 1. This one is coming from here, this one is coming from da da da. And actually it's plus minus 1. Well, that means the only candidates are plus 1 and minus 1. But we have already established there are no negative real roots, there's no positive real roots. That means this is not a candidate. So the only candidate is this, correct? Well, let's try. Let's try q minus 1. Well, remember this is the polynomial we are looking at qx, x cubed plus x squared. Well, that is minus 1 cubed plus minus 1 squared minus 1 plus 1. Oh, that's minus 1 plus 1 minus 1 plus 1 equals 0. That means minus 1 is a root of qx. That means qx equal x minus minus 1 times some other polynomial mx. So that means x cubed plus x squared plus x plus 1 equal x plus 1 times mx. And you'll say, wait a second, I already knew minus 1 is a root. Because remember when we substituted here, we said minus 1 is a root. But be careful, minus 1 was a root of this big polynomial, but we also found minus 1 again is a root of qx. That means minus 1 is twice. It has a multiplicity of 2. Does that make sense? That means fx was equal to x minus 1 because 1 was a root, x plus 1 because minus 1 was a root, x plus 2 because that was a root, multiplied by qx. And we had established that qx was equal to x cubed plus x squared plus x plus 1. But we found that that qx itself is equal to, so I'm going to borrow all three of these guys. These three things multiplied by, we are saying qx itself is some factor of x plus 1 times some new polynomial mx. So this is what I mean by that minus 1 is coming twice. How do you find mx? Well, you can do synthetic division, you can do long division, but I want to show you one other trick. Remember we said qx equal x cubed plus x squared plus x plus 1? Well, what happens if I take this as common? I rewrite this as x squared, x plus 1. Well, that's almost this. Well, this is 1 times x plus 1. And now I can take this as common and combine these. So this equals x squared plus 1 times x plus 1. So I just wanted to illustrate that qx, which was equal to this, we found x plus 1 is a factor. We could have done division of qx by x plus 1 and found mx. But there's a shorter technique in this case. It just worked. That means mx equals x squared plus 1. So now finally we have taken care of the entire factorization. I have a fx equal this times x plus 1 times x squared plus 1. Or I can say this x plus 1 is coming twice, so this is the multiplicity of 2 times x squared plus 1. We took a very complex polynomial, which was of degree 6. This polynomial, this is not a trivial problem. We took this polynomial and we actually found a way to factor the whole thing. We have found that this entire polynomial can be factored as this. So what does that tell me? It tells me my roots are from here here, 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 and here. By the way, let's just solve this one, this puppy. X squared plus 1 equals 0, x squared equals minus 1, x equals plus minus I. Do you see that? Because that's x is simply square root of minus 1, which is plus minus I. Correct? So my roots are 1, minus 1, minus 1 twice, minus 2, I, minus I. And the reason I wanted to highlight this is 1, 2, 3, 4, 5, 6. That means I have 6 roots for this polynomial, which is exactly what I wanted because it has a degree 6. So we found the root. Now, can we do the graphing? Yes, this is easy now. This is very easy now. Well, in order to do the graph, I know my end behavior. Because we are talking a polynomial degree 6, even power, that means very large x, positive number, very negative x, positive number. We also know that it is going to have an intercept when x is 0, it's going to be minus 2. We know that, right? We know the roots. We have some idea. We know 1 is a root. We know minus 1 is a root twice. And we know minus 2 is a root. And we are not going to worry about I because we are dealing with only real values of x-axis. So what are the candidates? What are the possible graphs? I know this graph has to come down somewhere like this. I'm going to drawing only approximately. It comes up to here. This is the intercept. This graph has to come down from here. Now there are a couple of possibilities. See, if it comes down here, and I'm going to illustrate, if it comes down here, I can't take it up. Because if I take it up, then how do I bring it down? Because that will end up creating one more root which I don't have. That means this is wrong. This possibility doesn't exist. Correct? We cannot accept this behavior. What can we accept, however, is that maybe, how is that possible? Well, maybe what it does is this. It goes up and then it just comes back. That is a possibility, right? That it goes up, but it does not cross. It simply comes back. That will give me the end behaviors. That will give me the intercepts here. It will give me root of minus 2, minus 1, 1 root. Everything will work. But is that the behavior? Is that the only way we can draw this graph? Is there any other way we can graph it? Yeah, there is another possibility. And we don't know which one it is until we do some more calculation. So I know I have my roots at -2 and -1, and I have a root at 1. I know I have an intercept here of this thing, and I know the end behavior is such, right? So let's draw the portion of the graph that we know for sure. This comes here, this we know. This comes here, this we know. And as I said, once you cross this line, we have to find a way. So, well, maybe it doesn't cross the line. Maybe it simply goes like this. So what do I have? I have an end behavior for negative infinity. I have an end behavior for positive infinity. I have a y-intercept. I have a root here at 1. I have another root at -1. I have another root at -2. Actually, -1, I have two roots. And that behavior will make sense too, right? So which one of these is? Now, there is absolutely no way you can calculate this unless you calculate one of the values. And which value you want to calculate? You want to calculate the value which zooms in into this zone. You want to zoom in here, right? You don't have to do anything else. You just have to zoom that in. So what's a good number? All I have to do is calculate f 1.5. And I'm not going to do that in my head. It's just not worth it. But you put in your calculator and you calculate f1.5, and you will find that it has a graph. Actually, I have shown this. If you do this, it will have a graph which is going to look like, I inputted this function by the way. Notice x to the power 6 plus 3x5 plus 2x to the power 4 minus x squared minus 3x minus 2. Well, Wolfram alpha is, I love it. It tells me that if I take a graph of this, it's calculating, and it's going to look like this. Remember we said there were two candidates? In one case we were coming down and going back up. Well, that's exactly what is happening here. It comes down from 2, it comes over here, it goes down, it goes back to 1. It does not cross 1, because if it crosses 1, it will end up creating another real root. And then it comes to -2, and then it goes to 1, and the end behavior is right. So this is my graph, and I got that, and that tells me what I had here, which was, it is this behavior that we are looking at it. So when you do the calculation, it turns out this is the right answer. Now notice how we went through so much work. We started with a function. It's like a 3-page problem almost. We started with a function, in this case. Where is mine? Here it is. We found the end behaviors. We found the y-intercept. We found the sign changes. We found there was one positive real root. When we used -6, we found 5 sign changes. That means there were 5 or 3 or 1 negative real roots. We used the fraction theorem. The coefficient here was 2, and we found the factors, and we went through all that, and we found some roots. Then we multiplied these roots. We did a long division. We got that. Then once again we applied the sign change and we found there were no negative real roots for qx. Then we found there's 3 or 1 negative real root, and we applied, and we found all that, right? And we found the roots v1, minus 1 twice, minus 2, I and minus I. A lot of work, right? Well, guess what? If you had gone to Wolfram Alpha and you had inputted this function, which I did, and you would have found it gives me this is the function. It gives me a graph, which if you zoom out looks like this. It gives me factorization. Right here, x minus 1 times x plus 1 squared times x plus 2 times x squared plus 1. These are the factors. That tells me roots are 1, minus 1 with a multiplicity of twice, minus 2, and I and minus I. So of course there are computers that can actually help you do this real quickly without any problem. But the fact is that when you are looking at it, building those computer programs, etc., you need to know this math. And that's where it is kind of fun, that once you know these techniques that we have talked about, you can even find root of something which is so complex looking as the one that I have. Hope this helps. And this was a long session, but I think with this you should be able to find the roots of most polynomials, at least polynomials that are going to be part of the test. For some of the real life stuff, you have no choice except to use the computers and graph and all that. Okay, have fun.